Okay, we're gonna finish up our endocrine system today. We're gonna start with a quick review of some of the hormones we went over last time. We're gonna start with our gentleman. Doesn't know me by name. Gonna start with a review question on thyroid hormones. So if you want to take a quick peek at those before we get started. All right. Well, that's not working today, so we are not going to answer that question. Hopefully the later ones will come in. There's just something wrong with that one. So we'll do a drawing and review these because I was going to do it anyway. All right. So two of our main hormone pathways we went over last time were our thyroid hormone, how we produce that. We also talked about cortisol secretion. Okay. So for both of these, we're going to involve tropic hormones, first coming from the hypothalamus, and then coming from our anterior pituitary. All right, so let's do thyroid first. So the point of thyroid hormones and the calorogenic effect, which is this is to help you metabolically. So when they test your thyroid levels, if you go into the doctor feeling lethargic, maybe gaining weight, one of the reasons they test thyroid hormones is that these are regulating how we burn calories in body. Okay, so that's the point of a thyroid hormone. So how do we get it? So we're going to start up in the hypothalamus. So I'm going to draw a little hypothalamus here. And we're going to have a pituitary sitting below. Okay. So what we were talking about is that because this is an anterior pituitary hormone, we have a kind of long pathway. So in order to release thyroid hormones, we're going to start with a tropic hormone in the hypothalamus up here in the brain. So that's going to be our thyroid releasing hormone, our TRH. Okay. So we got neurons in the hypothalamus. They're releasing this into the bloodstream, but specifically, they're releasing it into one little capillary bed up here. We have a portal system with another capillary bed down here in the anterior pituitary. So that's how they get there. So our TRH is getting to our anterior pituitary. That's the tropic hormone. So the next thing it does is affect the release, right? That's why we have a releasing hormone of an anterior pituitary hormone. Okay. So next we have our TSH, our thyroid stimulating hormone. So the thyroid stimulating hormone, job is to stimulate the thyroid gland, telling it to release the two thyroid hormones we talked about when we looked at the gland itself. So we're going into our systemic circulation. We're going down, down, down to our thyroid gland, down kind of in the neck, the base of the neck area. Okay. We know if we zoom in on the thyroid, we have multiple types of cells. So we have follicular cells around the edges. We have colloid area inside. Right, so in that inner kind of gel, we're waiting with a precursor molecule, which is called thyroglobulin. When that TSH comes along and gives us the signal, we tack on some iodine to that thyroid globulin and release our T3 and our T4, our two thyroid hormones that then go to the tissue and actually do their effects, create this calorogenic effect, help you burn your food efficiently. Okay, so that's one thing we went over. The other hormone we focused in on, here, it's fine, was cortisol. So we're doing the same thing when we think about cortisol. So cortisol is a hormone of stress. It's released during our fight or flight response. Also happens to lower the immune system activity, which you might link up with when people get like cortisol shots in a joint that's aching, reduce some inflammation there. So this is also controlled by the hypothalamus and the anterior pituitary. Okay. So from the hypothalamus, we have a releasing hormone, or corticotropin releasing hormone, or CRH. Okay. So that's in the hypothalamus, enters the first capillary bed, goes through the portal vein into the second capillary bed in the anterior pituitary. So we have our next hormone, our ACTH. Okay. So that's our adrenocorticotropic hormone. So it has that T in there for tropic because it is itself a tropic hormone. They tried to tell you some information about it in the name. Okay. So its job is to head to the adrenal gland. Okay, so our adrenal gland sitting on top of a kidney. A little hat. There's a kidney. Okay. We know that we have an adrenal cortex as well as an adrenal medulla. So we've got an outside and an inside. So that ACTH specifically is telling our adrenal cortex, right? Cortex to release cortisol. Bless you. So these were two of our examples that we went into in detail to kind of examine how the hypothalamus and the anterior pituitary work together and how have these domino effects of hormones when we think about tropic hormones and control of hormone release more generally. Okay, questions about these topics? So when you're practicing using that chart that we have, in the purple on top, you have the hypothalamic hormone. In the orangish peach layer, you have the anterior pituitary hormone. And then below that, you have the effects. But all you would be doing if you're quizzing yourself using that chart is doing things like this. So they're all going to work roughly the same way, though not all of them end up being tropic hormones from the anterior pituitary. So the hypothalamic hormones, not always tropic hormones that are going to the anterior pituitary. Some of the anterior pituitary hormones go directly. So that's where we were before. And we had talked about the fact that the cortisol that we were releasing at the end of this last example is part of a larger system. So we have lots of effects that go together under stress and stressful conditions that we refer to as a general adaptation system that help you respond effectively in kind of dangerous or high arousal excitation situations. So we increase a bunch of hormones related to this fight or flight response. So we're increasing cortisol. So that's going to help you get energy because it also has metabolic effects. We're going to increase sympathetic activity. So that's one of the two branches of our autonomic nervous system, also associated with this fight or flight effect. Okay. Mostly the sympathetic nervous system is releasing norepinephrine, but it's also hooked up to the adrenal medulla, so that inside part of the adrenal gland, releasing epinephrine. So epinephrine is like what you're injecting people with when they're having an allergic reaction, give them an EpiPen, right? So this is associated altogether with this response. We have a couple other hormones that are increased during this response as well. So ADH and angiotensin 2, we'll talk about in more detail next semester. Our overall goal is to respond to some kind of a threat, be it real threat or some threat that your brain is perceiving. So we need to mobilize our energy stores. We need to make energy available in the form of ATP. We're going to keep our blood pressure up. You want lots of blood flowing to your muscles so that you can actually do stuff. So this is helpful if you are in an actual stress situation or if you're going on a runner. So next, we're stepping into another gland. So we've been moving kind of down the body. So we talked about the thyroid glands in the neck. Then we are focusing on the adrenal gland on top of the kidney. Now we're moving to the pancreas. So the pancreas also in the abdomen. Pancreas is tucked here underneath the stomach. And we're going to see that the pancreas has a bunch of effects related to digestion, regulating in general, effects you want to have happen throughout the body when you're eating versus when you're not eating. That's going to be one of the big jobs of the pancreas. So that you're aware, the pancreas is actually kind of complicated. It does have multiple effects here. So it actually has, in addition to the endocrine part, so the hormonal part, also has an exocrine. The exocrine pancreas is having really local effects. So endocrine system, we're thinking getting into the bloodstream, going to distant parts of the body. The exocrine pancreas, we're going to be thinking about ducts going basically right here to your GI tract, so to the stomach and the next little bit called the duodenum. Okay. So the exocrine pancreas, which we'll talk more about next semester, has acinar cells and duct cells in it. Their job is to make a bunch of enzymes and fluids that help you digest food. So they go into the digestive tract through pancreatic. So that exocrine pancreas does make up most of the body of the pancreas. But when we think about the endocrine part, which is mostly what we're focusing on here in this unit, we're going to be looking in these little islands called islets of Langerhans. So this is where we're going to find our endocrine cells in the pancreas. So here's a cartoon version of that little islet of Langerhans. So we've got different types of cells in here. Okay, so in yellow surrounding, you can see the other parts of the pancreas. So this is that exocrine pancreas surrounding. So that's not involved with the hormones we're about to talk about. That's where you'd be making enzymes and putting them into ducts and sending them towards the food you're digesting. We're thinking about this stuff on the inside. Okay. So we have alpha cells. So you can see these alpha cells in a kind of blue color on here. So you can see them kind of scattered around. We have beta cells. So the beta cells here are the ones in green. And you can see there are more of them around here. We also have some other types of cells. So we have these long bluish purple delta cells. Okay. And we have these red F cells. Okay. So all these different cell types have different jobs. We're going to associate them with different hormones, different molecules. But we're mainly going to be focusing on those first two. So this is your total rundown. So your alpha cells are going to secrete glucagon. We're going to talk about glucagon in detail. The beta cells, the green ones, are secreting insulin. We'll also be focusing on insulin in detail. The other two molecules here, we're not really going to focus on past this slide, but just so you know, the delta cells make something called somatostatin, and our F cells make something called pancreatic polypeptide. Those we're going to leave for later. So when we're thinking about those alpha and beta cells and thinking about glucagon and insulin, these are two hormones that are going to control a lot of cells in your body actually during these two states. So we're going to see that your body is always either in the absorptive state or the postabsorptive state. And those two hormones, glucagon and insulin, are going to be associated with one or the other, changing how your cells kind of act. Okay. So both of these states are related to whether you're eating or not. Right? So these have to do with food, have to do with energy processing based on whether you have recently eaten or whether you haven't. Okay. So during the absorptive state is going to be when you just absorbed a bunch of stuff from the food you've eaten. You're going to want to store that. You're not going to immediately use all the energy in that food. Right? You don't want to have all your energy just in the half hour after you ate and then be like comatose for the rest of the day. So during the absorptive state, we take our excess nutrients and we store them into larger molecules. We put them in macromolecules so that we can use them later. So we're packing them into macromolecules so that we can use them later. And later is the post-absorptive state. So post-absorptive, after absorption, is when we're going to take those macromolecules. You haven't eaten in a while. We're going to break down those macromolecules and get energy now that we don't have it immediately available to us coming directly from like our stomach. So when we're thinking about the absorptive state and the post-absorptive state, we're going to be doing a bunch of compare and contrast. So in this unit, we have a lot of kind of compare contrast topics. And one big one we went through, right, was our sympathetic, parasympathetic parts of the nervous system. Hormones where we're comparing anterior pituitary, posterior pituitary. Now we're going to have absorptive state, post-absorptive state. Okay. So if we're thinking about the absorptive state, this is when we've just taken in a bunch of nutrition. We're trying to build macromolecules for storage. Okay. So one way we can think about this is that we have put more energy into the system than we're actually using. Right? You are not using all the energy in a giant bowl of Olive Garden pasta right there at the table. So your energy input in terms of the energy stored in those molecules is greater than your output, right? So you're not on a run while you're eating. Okay? So this means we have extra energy. Okay? We're going to store that extra energy. This also means that we have energy freely available in kind of easy to process forms. If you've just absorbed the nutrients from your food, you're going to have glucose swimming around in your blood. Okay? So you're going to be able to use that glucose for all your cells because you've got lots of it swimming around. It's freely available. Okay? And we're taking anything extra up and storing it, but we're also just using our easiest form of energy. Our easiest form of energy is glucose. That's our starter molecule for aerobic cellular respiration. When we think about what's extra, right, any extra glucose is going to get stored in our glucose storage molecule. Our polysaccharide, glycogen, is basically a bunch of glucose monomers linked together. Okay? So that's going to get stored in the liver and in muscle. And your lipids, especially your triglycerides, so those are like fats and oils, they're going to get stored in adipose tissue, so in fat tissue as well. So here we can see a diagram of what's going on with our different types of molecules. So you ate some food, and your digestive system and that exocrine pancreas help you absorb food that's gotten broken down into smaller nutrients, so into little bitty parts. So you broke down some carbohydrates into glucose. You broke down your fats into fatty acids. You broke down proteins into amino acids. Okay. And so now we're going to send those places. So our glucose is in part going to go just all around the body so that you can make ATP. Okay. So most of your body cells are getting that glucose so that we can break it down. Here are our byproducts, our CO2, our water, and our energy in the form of ATP that we talked about when we talked about metabolism. Now, we have some things that are going on in specific places. And when we think specific places, we're going to be looking at the liver and muscle cells. And we're going to be looking at fat cells. And those are our main kind of other places that are doing other stuff. So in the liver and muscle, we're taking that glucose and we're linking it together into glycogen molecules. In the liver as well as in the adipose tissue, we're taking some parts of that glucose, linking them together with fatty acids. That's going to give us glycerol. So that glycerol backbone comes from like the carbohydrate part, plus our fatty acids, okay, come from the fatty acids that we just absorbed. We're linking them together into triglycerides. So that's that flag-looking molecule with its glycerol backbone and its 3 fatty acid tails. Okay. So triglycerides, fat, this is kind of where we're storing them. The amino acids, so the proteins that you broke down, are also going to the liver because it can convert them into fatty acids and put them into some fat molecules, as well as to the muscle tissue and some of your other cells, which are going to take those amino acids and build them back up into proteins, right? So we're going to build proteins that do all sorts of stuff in the cells. So this might be part of your muscle tissue itself, the contractile part, might be building cellular machinery out elsewhere in the body. We're not being specific here, proteins of some type. That's during the absorptive state. So the absorptive state, you just absorb nutrients, you eat them really recently, and we're putting them into these larger molecules. This is like an anabolic state, right? Because anabolic is building things larger, building up big molecules. Our opposite is the postabsorptive state. So in the postabsorptive state, you're still using energy, so you still have output, but you're not taking in energy anymore, right? You absorbed everything already during the absorptive state. So now you have a low energy input, but you're still doing stuff out in the world. You still have significant energy output, right? So this means we're going to need to like budget our glucose, budget our energy as a body. Okay? We're going to see that we're going to keep any glucose that we still have swimming around for our nervous system. The nervous system in general really prefers glucose to other things, and especially the brain. So the brain really likes glucose. It's not going to break down a triglyceride. It's not going to break down proteins for energy. Use a little bit of ketones, but really glucose is its favorite, and that's kind of it. Okay. So because that's kind of it, any glucose we have, that's where it's going to go. Which means that your other cells are going to be using other stuff. And in general, we're going to be breaking down our larger molecules and getting energy out of them however we can. So our other tissues are going to be breaking down fatty acids. Don't have enough fatty acids, they'll be breaking down proteins. Are going to be breaking down all kinds of stuff. Okay, so here we have a diagram of all those things. So in general, we're thinking about breaking down big molecules, macromolecules that we stored earlier. So we might have proteins in the muscle and other cells. So we could break down proteins into amino acids, right? In which case, we'd start to see the level of amino acids in the blood go up as we break that down. In our fat tissue, our adipose tissue, we've got our triglycerides, so our fats. Okay? So we're going to break those triglycerides down into fatty acids and into glycerol. Fatty acids are going to go, some of them directly to the blood, some of them to the liver. Okay. And that glycerol is gonna go over here to the liver, but we'll talk about what this is doing in a second. Okay. So we see fatty acid content of the blood going up as we're breaking down our triglycerides. We'd also see ketone content of the blood go up. That's one of the byproducts when the liver breaks down your fatty acids. Okay. Now we're going to think about what's going on this side. Okay. So one of the things that we're doing, especially in the liver, but also a little in muscle cells, is we're going to be getting glucose from other molecules. So both the liver and the muscle have glycogen stored in them, right? So glycogen is that storage molecule for glucose. So we can break it down into glucose. Right? Liver is doing that kind of directly. Muscle does it in a little bit of a different way. We have some byproducts along the way, or lactate and pyruvate. So eventually we're getting glucose. The other thing that the liver can do is build new glucose. So we're going to be doing some gluconeogenesis. So making new glucose. And that's part of why we need this glycerol, right? So we gave the liver some glycerol, right? So we're going to be giving the liver some components for building new glucose, okay, which is going to raise the glucose content of our blood. Okay. So this is how we're getting molecules into the blood that we can use for energy, even though we haven't just eaten. Okay. So in our nerves and in the brain, we're going to really be using that glucose for energy, as well as some of those ketones, right, potentially. And everywhere else in the body, you're using the other stuff. So maybe you're using the amino acids, you're probably using some fatty acids, maybe some of those ketones. We're breaking those down for energy in the rest of the tissue. Here we go, right? Because we've just said that this whole process with the absorptive state and the postabsorptive state, it's involving all the cells in your body, involving your brain, it's involving your liver, it's involving your muscle, it's involving your fat tissue, right? So all those cells are going to need to know, what am I doing? Am I building bigger molecules, or am I breaking molecules down? Okay. So that's where the endocrine system comes into play. The endocrine system and these two hormones, insulin and glucagon, are the signals out to all those different cell types, telling them, are we in the absorptive state or are we in the postabsorptive state? So our hormone regulation, our insulin is going to be our hormone of the absorptive state. So insulin is going to be released after you eat food to tell the rest of your body, hey, we just ate food, get ready, pull that stuff into your cells and make bigger molecules. That's insulin's job. Okay. Glucagon does the opposite. So these are antagonizing hormones. They have opposite effects. Okay. So glucagon is going to get secreted when it's been a while since you ate, getting kind of hungry, you don't have that much glucose left sitting around, then you're going to release glucagon from your pancreas. It's going to go out and tell your cells, hey, stop building molecules up. Now it's time to break them down. We need more energy. And that's the big point of these two hormones. There are some other hormones that are slightly involved in this regulation. Epinephrine in the sympathetic nervous system can be like a little linked, but it's really insulin and glucagon that are doing the bulk of the work. So that's what we're going to be focusing on here. So since we just talked about it, great, this one works. Right. So based on that stuff that we just talked about, when are we going to see insulin production and insulin secretion going up? Which of these situations?
right? Another second to choose, 50-50. All right, cool. Yes. So we're describing here in this answer the absorptive state, right? So you've eaten, not chewing anymore, but your belly's full, your blood is getting full of those small nutrients. You're going to want to release insulin to tell your body, hey, you can use the glucose for energy right now, and also take all that extra stuff, store it away for later. Perfect. All right, so that's insulin's job. So if we look at insulin overall, we know where it's coming from, right? So we saw where insulin came from here in those beta cells, right? So the beta cells in the pancreas are responsible for producing the insulin and secreting it. So they make it in their cells, they put it into your bloodstream. In those islets of Langerhans, in that endocrine part of the pancreas. Okay. And we know that their job is to tell the body that it's time to make those macromolecules. We've got extra energy. So we think of this as anabolic processes. Anabolism means building up things bigger from a chemical perspective. So we're taking all that excess energy, and in particular, we're putting it into glycogen, our storage molecule for carbohydrates, all those glucose monomers linked together. And we're making triglycerides and putting them in our adipose tissue in our fat. Okay. So we're storing glucose, we're storing fats in particular. We've got lots of nutrients available to us during this time period. So this means that we should probably have plenty of glucose around. So we're going to take glucose and use it anywhere we want in the body. Okay. So we're actually going to be promoting all of those cells. We're going to be telling them, yeah, it's fine, suck up the glucose, right? Take it out of the blood, put it into the cell, break it down for energy if you want. So we're going to see decreases in all the reverse processes. So catabolic processes are ones that break stuff down smaller, right? So anything that breaks stuff down smaller from a molecular perspective, we're decreasing that. So it wouldn't make a ton of sense to be building up glycogen while we're breaking down glycogen, right? So this is just kind of a logical step here, hopefully. Okay. So our insulin is our hormone of the absorptive state, which means that if you were tracking your insulin levels, they should be going up during the absorptive state, telling your body to do all this stuff. Okay. So how does your body know it's time to secrete that insulin? So right after you've eaten, we're going to imagine we've got some blood lying along your intestine. What color am I going to make your intestine? Okay. You got a tube for the intestine. Okay. All right. So as you eat that food and it goes through your digestive system, we're going to be taking things into the blood, right? So we've moved glucose in to the bloodstream. We've moved our amino acids into the bloodstream. And we also have some signaling going on. So we know that the parasympathetic branch of the autonomic nervous system is the rest and digest branch. So we also know that your vagus nerve goes all the way into the abdomen. So that's one of the named nerves that might be associated here. So the parasympathetic nervous system is activated. So there's a little nervous signaling going on here as well, telling us that we have started the absorptive state. And we have another hormone that we're not going to talk about in detail particularly, but you can know it exists. Maybe come back to it when we talk about digestion in A&P2. This glucose-dependent insulinotropic peptide, GIP, is basically a hormone telling our body it's time to release insulin. Right, so you can see this insulinotropic inside. Right, so it's a tropic hormone. Its job is telling you to produce insulin. So the other thing that's happening, as we have our parasympathetic nervous system, its activity increasing, because we're in this rest and digest state. We have dual innervation, right? So we got to dial down our sympathetic nervous system and epinephrine, which is usually being released at the same time as we have sympathetic activity. Okay? So we're decreasing all those postabsorptive things. So here we can see some of the signaling, right? So when we secrete insulin, here you can see a different view of all those actions in all our different cells. Right? So in most of our tissue, we're going to be taking glucose into the cell to break it down for energy. We're going to be pulling in some amino acids so that we can make proteins, right? This is not a time that it would make sense to break down proteins if we're busy making them. So any protein breakdown that was happening during the postabsorptive state is now getting shut down. In our fat cells in the adipose tissue, we're taking fatty acids and we're making triglycerides. So triglyceride synthesis, making triglycerides, which means we should probably stop breaking down lipids, right? So we're going to stop doing any lipolysis, which is lysis, breakdown of the lipids. It doesn't make sense to be making lipids and breaking them down at the same time, kind of wasted effort. So liver and muscle, we're making glycogen, so glycogen synthesis. So we're going to stop breaking down glycogen. And this was one of our questions last time. The glycogenolysis is the breaking down glycogen. No point in doing that while you're making glycogen. And we have in the liver, we're again making some fats, right? The other thing that the liver is able to do is make new glucose, right? So gluconeogenesis. But in our absorptive state, we just ate a bunch of food that probably had some carbs in it. So we probably have glucose coming into the blood. That's one of our triggers for releasing insulin anyway. So we don't need to make new glucose if we already have it. If we just got an easier way of getting that glucose, we don't need to build glucose molecules. So we're going to stop doing the gluconeogenesis for now. Okay. So that's the absorptive state. Everything that's the opposite of that is basically the postabsorptive state. Okay. So insulin and glucagon are opposites of each other. So for glucagon, they're coming from our other important type of endocrine pancreas cell. So the beta cells are making insulin. The alpha cells are making the glucagon. Okay. Or in our absorptive state with the insulin, we're saying it's okay, all the cells can use glucose, we have plenty. Now that we're in the post-absorptive state, we're releasing glucagon. That's a no. We want all the glucose that we have to go to the nervous system because those nervous cells in the brain in particular are kind of picky. They really like glucose and they don't really like anything else. Okay, so we're going to be doing glucose sparing is the technical term for that. Sparing the glucose for the nervous system. So saving it basically. So glucagon is kind of controlling the post-absorptive processes. So glucagon is going to tell your cells, now it's time to break stuff down, right? So this is a catabolic hormone overall, right? It's telling the body to start breaking down macromolecules, right? So we are going to break down glycogen, so our glycogenolysis, right? Glycogen is where we store glucose. Now it's time to use it. Same thing for lipids. So probably our triglycerides, but in general, lipids, lipolysis. We're going to break down lipids, get energy for them as well. And since we don't have much glucose available to us in the blood right now, right, we didn't just eat carbs. in addition to sparing glucose for the nervous system, we're going to make some new glucose so that we can feed the nervous system even more. So gluconeogenesis, so creation of new glucose is going to happen so that we've got extra glucose for the brain or your nerves. So this is the antagonistic hormone to insulin, has the opposite effect, right? Doing catabolism, breaking stuff down, while insulin was all about anabolic metabolism, building stuff up. So, will you remind me, check that we were all on the same page. So what organ system do we need that glucose for? Where are we saving glucose for? And why are we making this glucose? Okay, final answers in. And now take a look. Okay. Yeah, it's our nervous system. So it's the nerves and the brain that need to use the glucose. The liver is part of what's making the glucose. Right? So the liver is making new glucose, but it's not because the liver needs to use it itself. It's making it so that we can continue to feed the nervous system glucose, even though we don't initially have it in the blood, right? We're not absorbing it directly from food during this time. Here's the rundown of glucagon. So glucagon, we're associating it with the post-absorptive state. The post-absorptive state, I think when you're hungry, you're in the post-absorptive state. Well after we've absorbed our nutrients and put them into our storage molecules. So during the post-absorptive state, right, when you're not in rest or digest mode, you're in the opposite mode. So our sympathetic nervous system is a little more active, probably producing a little more epinephrine from your adrenal glands. This is going to be some of the trigger for releasing glucagon, for glucagon secretion. This is kind of how the pancreas knows. Okay? And then this all decreases when we get back to the absorptive state. So you're hungry, you ate food, and that moves you into the absorptive state. Okay? So in the absorptive state, we're going to see that you are again going to have increases of glucose into the plasma. You have all those nutrients coming in. That's our trigger to stop making glucagon. So if we look at it in flowchart form, right, here are all the different processes that we want to think about and know whether we're turning them on or turning them off, right? So when we make glucagon, we're in the post-absorptive state, which means that anything that involves breaking stuff down is going to be associated with us. Anything that involves building stuff larger, probably not going to be involved, with the exception of, is this new glucose so we can keep feeding your brain? Okay. So we are going to start breaking down our glucose, right? So we can see that increase in glycogenolysis. So we're getting those glucose molecules out of the glycogen, breaking down that larger molecule into the smaller bits, which means we're not making glycogen, right? We don't have enough extra. We're breaking it down into its component parts. We are making some new glucose. This is the one thing that we would be making during the post-absorptive state. So the gluconeogenesis is making some new glucose so that you definitely have enough to fuel your brain, right? So you do want to make new glucose here. Ketones are a byproduct of breaking stuff down. So you would have some ketones being made as well. And also your nervous system can use a little bit of ketone for energy as well, right? So ketones are allowed. But on the whole, we're breaking stuff down. So we're breaking down proteins, which means we're not making proteins, no protein synthesis happening here. We're going to be breaking down our fats, lipolysis, not making fats, and we're not doing triglycerides. Questions about this? That is most of what we need to know. So I'm just going to do a little teaser of this for next time. This is where we'll pick up. So next time we'll be talking about how we have negative feedback loops and control. So the reason that, for example, diabetics need to check their blood sugar level is we have normal levels of glucose in the blood, right? Insulin and glucagon are kind of linked into glucose blood levels, right? So we're going to have definitions of if we dip in and out of that range, and we're going to be able to relate that to what's going on with our lives. But we'll save that for next week. All right. Have a great weekend, everybody. And the quiz is up, so make sure to get to that at some point today, over the weekend.